Welcome to the deep dive. Look around you right now. The chair you're sitting on, maybe the phone in your hand, even the air. Well, much of it connects back to one single element, carbon.
That's right. And today, we're taking a deep dive into the world built around that element, organic chemistry. Our guide for this exploration is a grade 12 physical science study source, specifically zeroing in on the chemistry of carbon compounds.
Okay, let's unpack this. The mission for this deep dive is to maybe cut through some of the complexity. You know, the naming, structures, properties, reactions.
Yeah, distill the essential knowledge from this source.
So you walk away with a clear, engaging grasp of these, well, fundamental organic concepts.
So where do we start? I guess at the heart of it all, the organic molecule itself.
Right. What is an organic molecule exactly?
Well, the source defines organic chemistry pretty simply as the chemistry of carbon compounds. You find them everywhere, living things, manufactured materials. So organic molecules, definitionally, contain carbon atoms.
Simple enough. Carbon's the key player. But the source mentions exceptions, doesn't it?
It does, yeah. Things like carbon dioxide, CO2, carbon monoxide, even carbonates and cyanides.
They all have carbon, but they're, not organic? Why is that?
It's a good question. While they have carbon, they kind of lack that core feature of most organic compounds, which is a backbone or chain made mostly of linked carbon atoms.
Oh.
Organic typically implies carbon bonds forming the main structure, the scaffold.
Okay, the linked carbon backbone is key. And within these molecules, there are specific bits that do the interesting stuff, the reacting parts.
Exactly. That's where the idea of a functional group comes in. The source describes it as a specific atom or a group of atoms within the molecule.
Okay.
This group is essentially the active part. It's responsible for the molecule's characteristic chemical properties, how it reacts. The source even shows a kind of general structure, hinting that a specific arrangement, maybe an oxygen and hydrogen on a carbon, is what determines how it behaves.
So the functional group is like the molecule's personality.
Yeah.
Chemically speaking.
That's a great way to put it. Yeah, it's chemical personality. And if functional groups are personalities, then a homologous series, well, that's like a family.
A family. How so?
Well, they all have the same functional group, so they have similar chemical properties, and they share a general formula. As you go from one member to the next, you usually just add a simple national CH2 unit.
Right, like adding another link to the chain, but keeping it in the same family type.
Yeah.
Got it. And we also need to get clear on saturated versus unsaturated. The source mentions this too.
Yes, this describes the bonds between the carbon atoms in the backbone. A saturated compound has only single bonds between the carbons. Think of them as saturated with hydrogens, holding as many as possible.
Okay. Single bonds saturated.
And an unsaturated compound has at least one double or maybe a triple bond between carbon atoms. Those multiple bonds mean they could potentially bond with more atoms. They aren't fully saturated yet.
Got it. Single bonds only, saturated. Yeah. Double or triple bonds present, unsaturated. And finally, structural isomers.
Isomers. These are fascinating. Structural isomers are compounds with the exact same molecular formula.
Meaning the same number and type of atoms?
Precisely. Same atom, same count, but they're connected in a different order. It's like having the same Lego bricks, but building two totally different things.
Huh.
The source mentions different types, like chain, positional, and functional isomers. Tiny connection changes can make entirely different molecules.
Okay, so those are the basic ideas. What makes an organic molecule? Some key terms. How do chemists actually, write these down and name them?
Right. Formulas and naming. The source covers different ways to write them out. There's the molecular formula, just counts the atoms, like C4H10.
Okay.
Then condensed structural formula, which shows a bit more connection, like CH3, CH2, FAH2, CH3 for butane.
Right, groups them together.
And the full structural formula, where you draw out every single bond.
Just a picture, basically.
Yeah, the full picture. And for this grade 12 level source, we're mostly looking at molecules up to about 8 carbons, and usually just one main functional group per molecule, though it notes haloalkanes can have maybe up to 2 halogen atoms attached.
And the main families, the homologous series we need to know.
Yeah.
Based on those functional groups.
Exactly. The source lists them. Alkanes, those are the saturated ones, single bonds only, no rings mentioned here. Then alkenes and alkanes, the unsaturated ones with double or triple bonds, again, no rings.
Okay.
Alcohols, they have the ITO-H group, the hydroxyl. Halocanes have a halogen fluorine, chlorine, bromine, iodine.
Right.
Carboxylic acids have that H group, the carboxyl group. Aldehydes and ketones both have a carbon-oxygen double bond, the carbonyl group, but its position differs.
And esters.
And esters, yes, often formed from alcohols and carboxylic acids.
It seems like you build them up. Start with a carbon chain, stick on the right functional group, and maybe add some smaller carbon branches. Alkyl substituents, the source calls them, like methyl or ethyl.
Exactly. Methyl is one carbon, CH3, branched off. Ethyl is two carbons, CH3CH2. The source mentions we might see up to 3 of these alkyl branches sticking off the main chain.
Okay, so you build the structure, then you need a name. The IUPAC rules.
Yes, the IUPAC system, International Union of Pure and Applied Chemistry. It's systematic. The source gives examples, asks you to name structures or draw structures from names. It really forces you to see how the name describes the molecule precisely.
Oh.
Well, the name tells you the length of the longest carbon chain, what functional group is present and where it is, and the type and position of any branches, those alkyl groups.
It's like a code for the structure.
Exactly. A universal language for chemists, so everyone knows exactly what molecule you're talking about.
Makes sense. Otherwise, it'd be chaos with potentially millions of compounds.
Absolutely. And understanding that structure, that specific arrangement and functional group, well, that's the key.
The key to what?
To predicting how the molecule behaves. Not just chemically, but physically, too.
Ah, physical properties. Like boiling point, melting point, vapor pressure.
Precisely. The source really emphasizes this connection. These properties are determined by the forces between the molecules.
Intermolecular forces, IMFs.
Exactly, IMFs. It's a powerful idea. These tiny interactions between separate molecules dictate whether something's a gas, liquid, or solid at room temperature, how easily it boils or melts.
Okay, so if the forces holding molecules together are strong,
then you need more energy to pull them apart, right?
Yeah.
To melt them or boil them into a gas.
it's higher boiling points, higher melting points, and lower vapor pressure, because fewer molecules can escape.
You got it. That table in the source summarizing it, strong IMF means higher boiling melting point, lower vapor pressure. That's a really core principle here.
It seems straightforward when you put it like that.
It is, conceptually. And the type of functional group has a huge impact on these forces. Take alcohols, for instance. The source points out their OH group allows them to form hydrogen bonds between molecules.
Hydrogen bonds, those are quite strong, right?
Yeah, very strong, relatively speaking, for IMFs. Now compare that to alkanes. They don't have groups capable of hydrogen bonding. They only rely on weaker forces, van der Waals forces.
Okay.
So think about ethanol, an alcohol, versus butane, an alkane of similar size. Ethanol boils way higher, like 78 degrees C. Butane boils around 0 degrees C.
Wow. Just adding that OH group makes that much difference.
It's a huge difference in physical properties. And it's not just the functional group, the chain length matters too.
How does that work?
The source explains it well. As the carbon chain gets longer, there are simply more points along the molecule where these intermolecular forces can interact with neighboring molecules.
So more surface area for the forces to act on.
Essentially, yes.
Yeah.
More points of contact. The individual forces aren't stronger, but the total effect adds up.
Like having more little Velcro patches along a longer molecule compared to a short one, holding them together.
That's a perfect analogy. More contact points means stronger total attraction, which is why, generally, as you go up a homologous series longer chains, the boiling and melting points increase.
And vapor pressure decreases.
Correct. And the source even hints at branching.
Branching, like those alkyl groups. How does that affect things?
Well, if you have isomers, same formula, different structure, the more branched molecule often has a slightly lower boiling point than a straight chain one.
Lower. Why is that?
Because the branches make the molecule more compact, sort of ball-like. They can't pack together as closely or efficiently as long, straight chains.
Ah, so the intermolecular forces aren't as effective over the whole surface. Less good contact.
Exactly. Reduces the overall strength of the IMFs between molecules.
So structure dictates the intermolecular forces, and the forces dictate the physical properties. Neat.
It's a really nice chain of cause and effect. And of course, these molecules don't just sit there. They react. They change.
Right, chemical reactions. The source mentions classifying them. Elimination, addition, substitution.
Those are the 3 main types, yes. Helps to organize the huge variety of organic reactions.
Okay, let's look at some specific ones mentioned. Combustion. We all know burning.
Right. The source defines combustion of alkanes as rapid oxidation. Usually needs oxygen. Produces carbon dioxide and water, typically. And it points out alkanes are used as fuels. Makes sense. Combustion releases energy and is generally irreversible.
Okay, burning fuels. What else? Ester formation.
Yes, forming esters. Esters often have fruity smells used in flavorings. The source shows a specific reaction. Propan-1-ol, which is an alcohol,
Okay.
reacting with ethanoic acid, a carboxylic acid. It says you need an acid catalyst shown as H plus water. And the products are the ester, called purple ethanoate, and water.
So alcohol plus carboxylic acid gives you an ester plus water, often with an acid catalyst.
That's the general pattern for esterification, a really important reaction type.
Got it. Now, what about those general types? Substitution.
Substitution. The source defines it as one atom or group being replaced by another, like swapping partners.
Okay, examples.
The source lists hydrolysis of haloalkanes. That's usually replacing the halogen atom with an OH group, often using water or a base like hydroxide. And also halogenation of alkanes, swapping a hydrogen atom on the alkane for a halogen atom, like chlorine or bromine.
Okay, swapping atoms or groups. What about addition?
Addition is characteristic of unsaturated compounds, those with the double or triple bonds.
Right.
You're adding atoms or groups across that multiple bond. The double or triple bond breaks, and you form new single bonds to the things you added.
So you're adding to the molecule.
Exactly. The source lists types like hydration adding water across the double bond, hydrogenation adding hydrogen H2, and hydrosalgination adding a hydrogen halide, like HCl or HBr.
Right.
There's an example. Prop-1 alkane, an alkane with a double bond, reacts with a hydrogen gas, usually with a catalyst like platinum.
And you get propane. The double bond is gone, replaced by single bonds with the added hydrogens.
Precisely. You turned an unsaturated molecule into a saturated one.
So if addition adds things across multiple bonds, elimination must be the opposite, taking things away.
You got it. Elimination reactions remove atoms or groups from adjacent carbon atoms, and this often forms a double or triple bond between those carbons,
Creating unsaturation. Examples.
The source mentions dehydrohalogenation of haloalkanes, removing an H and a halogen, like HCl or HBr, to make an alkene. Dehydration of alcohols, removing water, H and OH from adjacent carbons, also to make an alkene. And cracking of alkenes.
Cracking, that sounds intense.
It is, often involves high temperatures or catalysts, but it's incredibly useful.
Mm-hmm.
Cracking breaks large alkane molecules, which might not be very useful as fuels, into smaller, more valuable molecules.
Like what?
Typically, you get a smaller alkane and an alkene, sometimes hydrogen gas too. It's crucial for gasoline production from crude oil.
And how do you do it? The conditions.
The source mentions two ways: high temperature and pressure without a catalyst, that's thermal cracking, or lower temperature and pressure but with a catalyst, like platinum catalytic cracking. The examples show butane cracking into, say, hydrogen and but-1-one, or maybe into ethene and ethane, often shown with PT and a delta symbol for heat.
Okay, so you can swap parts, substitution, add parts to break multiple bonds, addition, or remove parts to create multiple bonds or break chains, elimination. That covers a lot.
Those are the fundamental transformations, and seeing these reactions, understanding the structures, the properties, it all connects back to the real world.
Right. It's not just theory. The source linked alkanes directly to fuels combustion. Cracking is how we get gasoline components.
And it even introduces polymers, plastics, huge molecules made by linking lots of small organic units, monomers, together. It briefly touches on different types, thermoplastic versus thermoset, and even shows images related to recycling. It grounds the chemistry.
It really shows how versatile carbon is, how these basic principles explain materials, energy, even aspects of life.
Absolutely. Understanding these core ideas from the study source gives you a foundation for so much more.
So we've taken this grade 12 source material and hopefully clarified the definitions, the structures and names, how properties link to forces, and the main reaction types.
It's definitely a foundational look. Organic chemistry is vast. I mean, the number of possible organic compounds just dwarfs inorganic ones. Carbon's ability to bond with itself and other atoms in so many ways, chains, rings, branches, different functional groups, it creates incredible diversity.
So the next time you fill up your car,
Yeah.
use a plastic container, or even just think about the chemistry happening inside you.
Mm-hmm.
Consider the amazing carbon atom and these principles of organic chemistry we've touched on.
There's always more to explore, of course.
Definitely a deep dive into the world built on carbon.